So I didn't have to miss anything.
All right, let's see. I need to share that. That's what I need to share. Let's see here.
Also, by the way, the videos are so boring.
I know. The thought of you having to sit through them and watch them kind of pleases me. Like, it's like, that's torture. That's payback. All right, so the things I was asked to cover a few things, and I think the first question I had was to talk about when a limit doesn't exist. And so there's really only like 3 or 4 reasons why a limit won't exist. So the first thing I would say is if a function is continuous. So like this function that we're looking at right here, it has a discontinuity right here, a place where we would have to lift our pencil to draw the picture. Well, if it's not going to be, if the limit isn't going to exist, the discontinuity is one of the places where it might not exist. But if you look at the function everywhere except at x equal to 1, the function's continuous everywhere else. So the limit is going to exist everywhere where the function is a continuous function. So like if I wanted the limit at 2, as long as I can establish some open interval around the number I'm interested in and recognize that on that interval the function is completely continuous, the limit exists on that interval, and it's just the function value. If I name this function f of x, then the function value f of 2 is the limit, as long as the function is continuous in a neighborhood around 2. So when we're looking for places where there might be a discontinuity, when we're looking for somewhere where the limit might not exist, we look at the discontinuities, and then we look at, we look at the discontinuities. That's the only place it might happen. So here's a place where the limit might not exist. And in this case, this type of discontinuity where the function value jumps is called a jump discontinuity, because the function is jumping from one spot to another, a jump discontinuity. And this is a place where the limit doesn't exist, because at 1, the limit exists for this, for this function, the limit exists everywhere. Everywhere, because this function is everywhere continuous except at x equal to 1. And this is going to be the only place where the limit doesn't exist. And the idea would be, is if I wanted to know the limit as x, as the inputs approach 1, right? So you approach 1 on the input axis from both sides. So if I want to know the limit of the function, say, does it exist? I want to look at the two one-sided limits. I want to say, what is the limit as x approaches 1, but approaches from the negative direction? So I'm not worried about this little arrow. I'm saying, hey, as I get closer and closer to 1, coming from negative infinity, is there a value that it looks like the function is approaching? An output value on the y-axis. And it looks like as you're coming in from 1 that the outputs are approaching 1, right? It looks like if I input 1, the output is 1. So the limit as you come in at x equal 1 from the left is 1. So this has a one-sided limit, or a left-handed limit in this case. But if you look at coming at the 1 from the other direction, so let's say I'm coming at it from this direction, so I would be asking, what is the limit as x gets closer to 1? What happens to the outputs as the inputs get closer to 1, but from the positive side? Well, does it look like the function is trying to approach an output? Well, yeah, it looks like it's trying to get a 2. It doesn't get there because there's a hole in the function right there. but it looks like the outputs are getting closer and closer to 2. So this is one where the limit doesn't exist because the two one-sided limits are not the same. They don't match up. The function isn't going to the same place regardless the direction at which you approach 1. If I'm approaching 1 from this side, I'm going to get close to a height of 1. If I'm approaching x from this side, I'm going to get close to a height of 2. So there isn't a limit, right? There isn't a limit. There are actually 2 one-sided limits, and the limit doesn't exist. Does that make sense or not make sense? It has 2 one-sided limits, but they're different. So there isn't a limit.
So what if that circle is closed? That open circle is closed?
There's still wouldn't, then there would be 2 things that I would say, Eva. I would say there would be 2 issues. If that was closed, there'd be 2 circles. Two problems. The limit as I approached 1 from the positive direction would still be 2, because this is the ordered pair 1, 2, right? But there would be a second problem. It wouldn't be a function because it wouldn't be passing the vertical line test. So it wouldn't even be a function. It has to have that hole in one of those 2 spots, or it's not a function. We have an input that's corresponding to 2 or more outputs. Violates the definition of a function, which says every input can have only 1 output. So the idea is you're going some, I mean, if you think of this as a hill, so I like to think of functions as hills sometimes. If I'm a person walking on this, and I'm walking this direction, which means I'm going uphill, and if I'm a person walking on this hill going up, will I wind up at the same place? And if the answer is I will wind up at 2 different places, then there's no limit. I don't wind up in the same spot. Is that okay?
That makes sense.
What was that?
That makes sense.
Oh, I thought somebody else said something. Maybe that was just garbled background garbledy-gook. So a jump discontinuity is a place where the limit might not exist. The limit doesn't exist because the function is trying to give you 2 different outputs at the same input. The other place that limits won't exist will be at discontinuities that are involving vertical asymptotes. So like if I look at this function, it's continue, you know, what is the domain of this function? Ooh, there's that domain word from pre-calc, right? You know, if this is the x-axis and the name of this function is f of x, then the domain is all of the possible input values x, right? Domain is what can I put into the function? And so what we would say is, hey, it looks like the function's coming from negative infinity in the x direction. So x is an element of the interval from negative infinity, and it's running all the way up to 2, but there's this asymptote here, so the function's never getting to that asymptote. So it's getting really close to 2, but it doesn't get there. And then the function jumps over it. And you'll notice, is there any way to draw this function without lifting your pencil? Can you draw this without lifting your pencil off the paper? Nope. Oh, I've got a discontinuity. The function isn't smooth and continuous. I have to lift my pencil to draw the picture. So it skips over x equal to 2, and then it picks up and it goes off to infinity. So any value of x in either of these 2 intervals, the function's going to have a limit. It's just going to be the function value. So the place where we have to look at the function to identify whether it has a limit or not is where we get this bad thing going on, this discontinuity. And so if I think about approaching an input of 2, but from the negative direction, from the negative infinity direction, I would say, hey, the limit, I'll write it over here. The limit as x gets closer and closer to an input of 2, but from the negative direction, the limit of my function looks, where does it look like it's giving, where does it look like the outputs are going? Where are the outputs going?
Negative infinity?
Negative infinity. So it looks like the limit is negative infinity. And I could actually stop right here, and I could say the limit doesn't exist, because a limit must be a number. And infinity is not a number. This function isn't going to give you a numeric output. It's just going to negative infinity. So right now I could already say the limit doesn't exist, because the one-sided limit here isn't a number. I could look at approaching the 2 from the other side just as easily. I could come in from this direction to the 2, and I could say, what is the limit as x gets closer and closer to an input of 2, but does it from the positive direction? What's the limit of my function now?
Infinity.
And then it'd say, yeah, it looks like the outputs are becoming infinitely large. So I could also conclude from that there won't be a limit, because infinity isn't a number. And I could further conclude that there isn't a limit because the two one-sided limits aren't matching. So I have more than one thing that lets me conclude that there isn't a limit. If I were writing this up in a homework, what I would say is, I would say something like this. If I were answering a homework problem and I were responding to it the way that kind of a math student is expected to respond, I might grab this or this, and I'd say, note that the limit as x goes to 2 from the positive direction of f of x is infinity. And I'm supposed to give graphical evidence, so I probably would say something even a little bit stronger. I'd say, based on the graphical evidence, right? Based on the graphical evidence, note that the limit as x goes to 2 from the positive direction is infinity, because the function outputs are going to infinity. Therefore, the limit does not exist. And I don't need to say that it doesn't exist because infinity isn't a number, because a consumer of math knows that infinity isn't a number, and a limit must be a numeric value. So for there to be a limit, the two one-sided limits must match, and they must be numbers. If you violate any of those things, you don't have a limit. And the only time a limit isn't going to exist is if you have a discontinuity of some sort. So even on this one, this is the function, I typed in the function 1 over x squared. The guy on the previous screen, he's the function 1 over x, but shifted. He's 1 over x shifted 2 to the right. So if you do a squaring, if you square negatives, it bounces the shape up. So this guy was 1 over x squared. I wanted to take that shape that wants to do this, and I just bounced him up. But it's still the same issue. You see that you've got this discontinuity here at 0. So I could say, hey, notice that the limit as x gets closer and closer to 0, as the inputs get closer to 0, for my function, I named them g of x, from the negative direction, so I'm coming from negative infinity, it looks like the limit is, hey, where does it look like the function's going?
Infinity.
Infinity. And the limit as x goes to 0 from the positive side, as I squeeze in from this direction of my function g of x, that limit is also going to infinity. So this is a case where the two one-sided limits are actually agreeing, but the limit doesn't exist this time either, because infinity isn't a number. You never get to a set output, so there is no limit. Does that make sense? So non-numeric limit means there is no limit. And then the other thing that can happen, this is a little less common, but the other thing that can happen is you can just get wild oscillation going on. So here, this is a function where as you get close to 0, the function just starts going bananas. It's going bananas. There's no limit because the function isn't settling in as you get closer and closer to 0. It doesn't settle in on a single value. So you could kind of experiment with this. So the function cosine of 1 over x right here is the guy I've got loaded into GeoGebra. Uh-oh, let me stop that share. Let me share GeoGebra here. All right. So here's one where you kind of get a graphical lie. You ready? Here's the function cosine. Yeah, I need to be, hold on 1 second. 1 second. I need to fire up, oh, where did it go? Holy schmack, where did it go? There he is. You can see GeoGebra okay? Can you see GeoGebra okay? All right. So this is the function cosine of 1 over x, right? And so right now I have the graph of it sitting here. So this is here to show you that you need to be careful when you're considering graphical evidence. Because right now, if I were to ask you the question, what is the limit of my function f of x, which is just the cosine of 1 over x? What is the limit of that function as x gets closer to 0 from the negative side? So as I come in from 0 from the negative side, what does it look like is going on? And then if I get, what does it look like the limit is right now? Anybody?
1.
1, yeah, it looks like the output should be a 1. So it looks like the function's trying to give you a 1. So, and it's not actually, this is a lie. And if you take the limit as x goes to 0 from the positive side of the function, so if I come in from this direction, it also looks like it's trying to give me an output of 1, right? It looks like the ordered pair 0, 1 is sitting right there. That's what it looks like. And the issue is I've scaled the x-axis, so the numbers are really big. So this is like zooming out into space, right? If you are on the International Space Station and looking at the Earth looks like a smooth marble. When you're far away from something, you don't see the surface features, right? When we look up at the moon, it looks pretty smooth. But it's cratered, and if you were on it, you would be having to walk up and down hills as you walked across the surface of the moon. So when we stand far away from something, it makes it look smooth. And so this is a function where if we, I haven't used this guy in a while. Where's my point? There he is. So this is a function where if I take and I zoom in closer to 0 so that I start to see that there's structure around 0. And this is where you're getting that wild oscillation. And so what you want to do is try to think about why this is happening. The key is to think about why is GeoGebra struggling so hard to draw this in? What's going on? And the key is to think about what's going into the cosine function right here. There's an input going into the cosine function the function 1 over x is going into it. So we'll call them g of x equals 1 over x. And what does the graph of 1 over x look like? The graph of 1 over x is undefined at x, so the y-axis is an asymptote, and the graph of it looks like this. Goes up to infinity here, and goes down to infinity here. So the key is that this function that's getting jammed into the cosine function, the limit of that function, the limit of the function 1 over x, as x goes to 0 from the positive side, is infinity. And not only is it infinity, but it goes to infinity really fast. It gets infinitely large fast. And if I approach, for this function, if I approach it from the negative direction, where is it going? It's going to negative infinity. But it's going there really, really fast. It goes there faster and faster and faster. And the idea is, when you have something like 1 over x, if you put numbers into 1 over x that get closer to 0, so like here's a number that's close to 0. 0.1 is a number that's close to 0 but isn't 0, right? Would you agree that 0.1 is starting to approach the number 0? Well, what does this equal? 10. Well, what happens if you put a number that's even closer to 0 in there? What happens now? What do you get? 100. What happens if you divide 1 by a number that's even closer to 0? What's that equal? 1,000. Does that make sense? Okay. What's that number look like? 1, 2, 3, 4, 5, 6. It's going to be 1 fewer zeros than 1, 2, 3, 4, 5. Poof. So what happens to 1 over x? If x gets close to 0, boom, it explodes. It becomes infinitely large, and it happens fast. Okay? So what's happening with this particular function is we have a number that's going to infinity really fast. And then we have to think about, what do we know about the cosine function? So the cosine function from trigonometry, what do we know about it? What's the outputs to it? It goes from what to what? What's the range of the cosine of x? Unmute and say the answer. What's the smallest number it can output? What's the smallest number that can come out of the cosine function?
Is it a -1?
-1, yeah, -1. And what's the biggest number that it can give you? What's the biggest number it can give us?
Is it 1?
Yeah, 1. 1, right? Remember, the cosine function is just the x coordinates on the unit circle. And where do the x coordinates on the unit circle go from? They go from -1 to 1. That's all it can give you. And how often does it give you those numbers? Well, it oscillates from 1 to -1 and back every 2 pi radians, right?
Mm-hmm.
Or about 6. So if the inputs are going to infinity, if the inputs are becoming infinitely large, how many times will you get 6 units? If 1 over x is becoming infinitely large, how many times will you get 6 radians?
You'll get an infinite amount of
You
cycles.
get infinitely many times you'll get 6 radians. And it's getting big faster and faster and faster. So you'll get 6 radians. Not only will you get 6 radians infinitely many times, but you'll get 6 radians faster and faster and faster and faster. So the function just sits and bounces between -1 and 1, which is all the cosine function can give you. It gives you numbers between -1 and 1. And if 1 over x is becoming infinitely large, it's going to give you 6 radians infinitely many times faster and faster and faster. And notice at 0, is this function undefined at 0? Yeah, because you can't plug 0 into that denominator. So we still have a discontinuity. So long story short, the question was, when do we have to watch out for discontinuities? The story is when do we have to pay attention to the limit not existing? And the answer is we look for discontinuities, places where we get, division by 0 or something bad going on, or a jump discontinuity. We look for vertical asymptotes. And those bad places are the places where the limit may not exist. It might, it could exist, but it might not exist. Is that okay? Maybe? Oh, come on. Gotta stop share for a minute. Oh, it's gonna be like that. Oh my word. Don't make me have to log out, and don't do it to me. Don't do it to me. Can I end it like this? There we go. Had to kill it the old-fashioned way. All right, where was? Show all windows. There we go. All right, I think I'm back in business. So anyways, those are the things to look for. Look for jump discontinuities. The limit won't exist at a jump discontinuity. Look for vertical asymptotes, where the limit is actually infinite instead of a number. Those are bad places. Look for places where you get wild oscillation going on as you approach a specific input value. Those are going to be the primary places where limits aren't going to exist. If the function's continuous, around the point at which you're interested in finding the limit always exists. This is just the bad places that you're worried about. And the reason we're worried about this right now is it turns out that calculus is going to require that we find a limit at a place where we have a division by 0. So calculus is driven by the ability to find out what happens when a division by 0 is going on. So we've got to figure out how to find a limit when a division by 0 is happening so that we can do calculus. So it's kind of a preliminary tool getting put in our pocket that's going to underlie the big definition of what a derivative is by next week. Eva, you asked for number 1 for me to talk about what the table should look like if you're doing tabular evidence for the limit in this case. So, and I noticed in the video, I don't think the guy took very granular steps in his approach. I think he took bigger steps than what I would be accustomed to taking. So if I'm looking at something, let's say I want the limit as x goes to 0, you need the 2 one-sided limits. You've got to look at the limit as x goes to 0 from the negative side. And you also need to take a look at the limit as x goes to 0 from the positive side. You have to look at it coming in on 0 from both directions. So what you want is numbers that get closer and closer to 0, kind of in the easiest possible way that you can do it. So if I were going to table this, there would be a couple strategies. I do it a little differently maybe than some books do it. So I like to say what limit I'm looking at. So this one I'm going to say, hey, I want to look at the limit as x goes to 0 from the negative side. And the numbers that I put next, I'm going to put them into the function. That's sad. And then I'm going to look at the other limit. I'm going to look at the other one-sided limit. I'm going to take the limit as x goes to 0 from the positive side. And the numbers that I put in the table, I'm going to put them into the function. So I would start off with something like that. And I know I'm not going to put 0 in, but I need negative numbers that get closer and closer to 0. So I would probably just do, hey, I'm going to do 0.1 as a number that's close to 0. What's a number that's even closer to 0? Well, put an extra 0 in there. What's a number that's even closer to 0? Put 2 little zeros in there. So it's a dime, it's a penny, it's not even a penny, maybe one more. Now I'm really broke. And now you just need the positive counterparts. So I'm just going to step over here and say, hey, I can squeeze in at 0 from the other direction. There's a dime. There's a penny. There's what the gas stations do. I don't know why. And I'm really broke. I don't know how much you could get with that much money, but it wouldn't be much, right? And all you do is pop those into the function. You just evaluate the function at those values. You put these numbers into this function and see what the outputs are. You put these numbers into the function and you see what the outputs are. And you try to identify, does it look like the function's trying to give you a specific number? And the way that you want to do this to make your life easier is you probably want to use a spreadsheet to do this, or the table tool in your Texas Instruments calculator. You want to use you don't want to hand calculate these numbers over and over again. That's tedious and unfruitful work. So what I would do on something like that is I would take a spreadsheet. And because I'm doing math, the spreadsheet that I like to use is actually the spreadsheet that is in GeoGebra. So I suggested, I think, getting the Classic 5 version, I think is what I suggested. And in the view menu here, in GeoGebra Classic 5, you have different options. Like you have their computer algebra system sitting here. You have a spreadsheet sitting there. And when you click into different things, the context menu changes to do things that are specific to the window that you're working in. So in spreadsheet view, which I just clicked into, it's actually giving me a bunch of statistics tools, because a lot of times you do stats if you're in a spreadsheet. I click into the graphing window, I get graphical tools, right? So what I would do on one like you were talking about is I would go ahead and make my tables. I'd say, hey, I'm going to let x go to 0 from the negative side. And then I'm going to evaluate my function there, right? So I'm just rewriting that table I wrote in the PowerPoint in red. I'm just typing in the headers. Probably really hard to see. How bad is it? I don't know. You're all muted, so even if you tell me it's bad, I won't know. So, not my problem. It's your problem, Eva. Then just type the numbers the numbers I wrote. You just type them. So this is -0.1, and then I did -0.01. And then if I try to do one more, I'm going to show you what happens. Negative 0.001. If I enter, it's just going to put a 0 there. And then you'll like be like, ooh, that's frustrating. That's not what I typed. But in GeoGebra, in options, you tell it how many decimal places you want to round to. So it's only set to round to 2 decimal places right now. So it just rounded my number. So I can go down and just say, hey, have more decimal places. And now I'll see it. And then, of course, you're always curious, can you drag it? No, it doesn't drag. So what do? We did one more number, 0.001. Somebody's texting something, but I can't read it. 1, 2, 1, 2, 3.
She asked if you're recording it so then she could come back and watch it.
I'm trying to record it. We'll see how that works. But I'm not recording it to the cloud. I'm recording it to my PC, so I'll have to upload it like into YouTube or something. And then right here, you just go in and I do have a recording going. I don't know if it's going to work or not, is what I'm saying. And then we had the positive numbers, right? We had, hey, do a dime, do a penny, do a fraction of a penny, and then do the point. And the thing that's nice about using, I need to throw you guys to another place on the screen now. The thing that's nice about using GeoGebra is I can type the function down into the input bar. So in the input bar, I can give the function a name, say f of x equals, and what was the function what was it? It was, what, x squared minus x in the numerator?
It was x squared plus x over sine x.
All right, so it's x squared. So I'm going to type that function in, x squared plus x, and then it's all over sine of x. So there's the function sitting right there. And you can see as x going to 0, what are you expecting to get for the limit? As x gets close to 0 from both directions, what does it look like the limit is?
1.
1. Looks like 1. So the thing that's nice about this is I can put an equal sign in the cell. I need to put these numbers into this function, but I just named the function f of x over here. So if I put an equal signs in and I do my function notation, f of parentheses, and then as long as I'm inside the parentheses, if I click that, you bugger, I go equals f of boom, and as long as I'm inside the parentheses with my cursor, see how I put the cell name in it? So now if I hit enter, it'll evaluate the function for me. And then if I click into the cell, I can just drag, and the rest of these numbers get evaluated. And then I go equals here, f of, and then put that, you bugger, equals f of, it's going to do it again, that's C, cell C3, enter, and it evaluates it. And then I can click in, hover over that corner, and drag, and it evaluates it. So I don't have to manually calculate the function at every value. And I know your graphing calculators, I think, have table tools in them as well, so you could do this type of thing. And then you just make a conclusion. As these get closer to 0 from the negative side, does it look like this number is getting close to something? 0.9999, that looks close to 1. And here it looks like the number is getting closer to 1, so you make your conclusion. So nothing magical about the tables. Nothing magical about the tables other than when you're doing them, you want to pick numbers that are getting close to the number you're interested in the easiest way possible. Easiest way that you possibly can. I think when I watched his video, I think sometimes he was like doing like increments of 5 or something, or I don't know. I think you look at the number you're interested in and just say, what's the easiest way to approach that number from both sides? I'm going to do that. Like if I needed to approach a 2, I would go 1.9, 1.99, 1.999. Hey, I'm approaching 2 from the negative side. Now approach 2 from above. What's a number that's close to 2 from above? 2.1? That's close. 2.01, 2.001. So just find a way to get closer and closer to your number in the easiest way that you possibly can. Does that answer your question, Eva? She's all muted. She's gone now. She's at the fridge, pouring a glass of wine. Who knows?
What are you talking about? I'm right here.
I'm talking smack about you. I said, did that answer your question? And you didn't answer.
Sorry, I'm spacing out.
I accused you of going and getting booze.
No.
No? Is everybody okay with that?
So is that what you want us to do on the homework, is make a table?
Well, for tabular evidence, that's what it's supposed to be, a table. And the question is, how are you going to organize your table? And I mean, some people organize them in a big long string this way. I think this is a nice way to organize it because I think it makes sense. But tabular evidence, yeah, you make a table, but I would use the spreadsheet to get the numbers that I put in here. I would use a spreadsheet, or I would use a spreadsheet and take a screenshot, right? I mean, there's nice ways to get those numbers without, otherwise you're dumping it in, having to calculate over and over. You know, what would this be? 8 calculations? That doesn't make sense. It's just tedious calculation. Have a spreadsheet do it, or some other computer aided tool. All right, so this one, was this the one, this was yours, Adon, wasn't it?
Yeah.
Yeah. So this is, so I mean, I guess I would ask on this one, was it a table that was bugging you? Is it the graph that's bugging you? What's bugging you?
Table.
The table? Because clearly there's a discontinuity. In fact, this is the jump discontinuity that we were just looking at. And the function GeoGebra didn't do it, but there's actually a hole because you can't plug in 2. You get division by 0. So like if you were hand graphing this, you would put a hole here and you would put a hole here because the function doesn't exist at x equal to 2. And if you're looking at the graphical evidence, you would say, hey, it looks like the limit as x goes to 1 from the positive side is 1. And it looks like the limit as x goes to -1 from the negative side, sorry, as x goes to 2 from the negative side is -1. So we have 2 different one-sided limits. For the table, I would do what we were just doing. I would say, hey, I'm going to plug in, I'm gonna take a look at, I'm gonna let x go to 2 from the negative side, and I'm going to evaluate the function there, and I would do something to make my life easier. I would say I might say let f of x equal x minus 2 over the absolute value of x minus 2. That way I can just talk about f of x. And then I would say, hey, let's take the limit as x goes to 2 from the positive side. And we know we need to put those numbers into the function. Now we just need to pick numbers that get, so for the x going to 2 from the negative side, we just need numbers that get closer and closer from 2 to 2 from underneath it. So to be underneath 2, I might say 1.9, 1.99, 1.999. That's getting closer to 2. Does that make sense? Getting closer to 2 from below. Yay or nay? Yeah? Okay. And then for this one, you just need to get closer and closer to 2 from above. So I need to start with a number that's bigger than 2. So I do the easiest number I can think of that's bigger than 2, and then I just force it to get closer to 2. There it is. And now you just need to plug these numbers into this function. And how are you going to do that, Adon?
What was the question?
I said, now you just need to put these numbers into the function. How are you going to do that?
Algebra.
GeoGebra, use a spreadsheet.
And for that problem, because this problem, the thing doesn't exist, is this the only ones that we like put reasoning why it doesn't exist?
Yeah, so you want to draw a conclusion from this. So this, you're going to get numbers that are going to be getting closer and closer and closer to -1. So I would say something like, after I get my table filled out, after I fill out my table, I would say something like this. I would say based on the tabular evidence, the table evidence, based on the tabular evidence, the limit as x goes to 2 from the negative side of f of x, and that's why I gave this function the name, so I don't have to write this whole thing out. I'd say, hey, it looks like that's -1, and the limit as x goes to 2 from the positive side of the function appears to be, and these are going to be numbers that are getting closer to 1, right? And then I would make a conclusion from that. I would say, because the two one-sided limits are not equal, because they're not the same output, the limit does not exist. Remember, the word "the" means it's singular, right? The is singular. And that's the key. That's the key with these limits. If we get two different numbers, we don't have a single number. We can't say "the." You know, we can say, well, there's two different one-sided limits, and they're both limits. They just aren't the same limits. So the function isn't going to the same place. And then, like I said, use a spreadsheet to get these, or use the table generating tool in your graphing. Use a tool so you aren't hand calculating this over and over and over again, which is just going to make anybody vomit. Are we okay with this one? And then Jasmine asked about this one. Is Jasmine around?
She said she had to go.
She had to take off. So now I don't know specifically what her question was. Like, I was able to ask you what was bugging you, and you said it was the table. So in this case, I'm not sure precisely what the question is. But if we were doing a table, I mean, this would be no different than the previous problem. I mean, we can see what the issue is. We have a vertical asymptote when x is equal to 1, because if you plug 1 into the denominator, what do you get? You get 1 squared minus 2 times 1 plus 1, which is 0. The problem with trying to find this limit, and the reason it might go wrong, is because we have a vertical asymptote there caused by the division by 0. That's what's going wrong there. And then if we were doing a table, we would play the same game that we just did. We'd say, hey, I'm going to take and look at the two one-sided limits. I'm going to take a look at the limit as x goes to 1 from the negative side. And I know I need to evaluate the function at those numbers I get. And then I want to take the limit as x goes to 1 from the positive side. And I'm going to evaluate the function at those numbers that I get. And then you're just going to make a table. And you're going to say, hey, I need to get close to 1 because I want to know the limit when x is equal to 1. So how can I get close to 1 from below? What's a number that's really close to 1? What's an easy number that's close to 1?
0.9.
0.9, exactly. That's like the easiest one to do. What's a number that's closer to 1? 0.99. What's a number that's even closer? 0.999. If you're going to do 4 of them, 0.9999. So just find a number that's getting close to 1 from below, and then for the other one, find a number that's getting close to 1 from above. What's a number that's just barely bigger than 1?
1.1.
1.1 is a beautiful number that's just barely bigger than 1. What's a number that's closer to 1?
1.01.
1.01, yeah, this is $1.10. Now this is $1 and a penny. So just cram zeros in and push this 1 further and further to the right.
Okay.
And you got a number that's getting closer and closer to 1. From above. So you need one set that's getting closer to 1 from below and one set of numbers getting closer to 1 from above. That's how you calculate the two one-sided limits. One's coming from above, 1 comes in from below. You come in at 1 from both sides, and then you calculate your limit. So again, what would be the easiest way to do this would be to get this function in GeoGebra and use the spreadsheet to generate these values, because calculating them by hand would be annoying and tedious. And nobody wants to do it, least of all me. I would find that uninteresting, horrifying, not a way I want to spend my Tuesday night. So you put them in the spreadsheet and then you draw your conclusion. And what you're going to see, what are you going to see when the numbers are getting in here? You're going to see these, you know, where's this going? Where's this function going? Well, you can see graphically, as you come in from this direction, it's going to negative infinity. So what we should see as we get numbers closer to 1, we should see big, bigger, 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 mega bigger. We should see numbers that get bigger and bigger and bigger, but they'll be negative. And then as we squeeze in closer and closer to 1 coming from this way, we should get big, bigger, even bigger, tons bigger, but positive because the function's going off that way. And so you'll look at that tabular evidence, and that's what you'll say. You won't even need to, it will wind up being the case that you don't even need to say something about both sides. You would be able to say, for example, the limit, you know, you would be able to say something like this: based on the tabular evidence, because you're going to have numbers getting increasingly large in here. Based on the tabular evidence, the limit as x goes to 1 from the positive side of the function is infinity. And then we can say, therefore, the limit does not exist. I don't even need to mention this side. And I don't need to mention it because infinity isn't a number, and if the limit exists, it must be a number. The moment either of the two one-sided limits is not a number, the limit doesn't exist. So, you mean you could have a function that looked like this, right? You could have a function that looked like, hey, maybe it comes up and it ends right here. Maybe there's a hole. In fact, maybe there's a hole right here. Let's do, whoop, here's a hole. Here's the vertical asymptote. Let's say this is at 2. And then let's say on the other side, the function looks like this. And let's say this input is a 1. So I would have the limit as x gets closer to 1 from the negative side of my function looks like it's a 2, which is a number. So maybe the limit exists. But on the other side, you would say, hey, the limit as x goes to 1 from the positive side, as we come in from this way, hey, my function's going to infinity. So the limit of my function is infinity. Hey, the limit doesn't exist because infinity isn't a number. Yeah, the two-sided limits don't match, but I don't even need to say that. I can just say, look, that one-sided limit isn't a number. There isn't a limit. Limits will always be a real number for the purposes of first-year calc. Is that okay? Any other questions?
On GeoGebra, for
Yes.
for the f of x input, how did you put that in so it can give you the numbers? I can see that.
So, all right, so let me hit escape on this. I'm gonna stop share on that. Share screen, share GeoGebra, share. Let me delete all of this crud out of here. There we go. So if you have a function, let's just say we're doing a basic parabola, x squared. In the input bar, down at the bottom of GeoGebra, can you see my input bar down here? Is it too far down?
I see it.
You can't? Can you see right here?
Yep.
So when you make a function in GeoGebra, what you want to do is use function notation. So something of x, f of x, h of x, r of x. It doesn't matter as long as you use function notation. So I could type h of x, where I'm using function notation. So the x is in parentheses. And then I type equals and I put x squared. And I hit enter. Oh, I see there, right there. There we go. Hit enter and there's my basic parabola, right?
Mm-hmm.
So because I used function notation, right, can you see h of x right here?
Yes.
That's what you want to use. So when I go into the spreadsheet, if I want to calculate some values, let's say 2, 3, see how smart GeoGebra is today. So I got 2, 3, 4, 5, 6, 7, and I want to calculate, I want to put these numbers into my function h of x. So what I do is I click into the cell, I go equals. I have to have an equal sign. And then I do h, and I open the left parentheses. And what you'll notice when you open the left parentheses is that GeoGebra automatically closes it with the right parentheses. And right now the cursor is inside of the function notation where the x would usually be. And now I just step over to the cell I'm interested in and I click it. And it will put the name of the cell. This is cell A8. So it'll take the value 2, which is in A8, and put it into my function h of x, which is the squaring function. So when I hit equals, I'll get a 4. And then once the spreadsheet knows what you want to do, if I click back into that cell and I get the square on the bottom corner, I just go over, I hover till I get the crosshair, and then I left click and hold, and I drag. And the spreadsheet is going to guess that I want to continue to feed the elements in this column into the squaring function. Microsoft Excel works the same way. The only difference in Excel is you can't make a function like this. So I would have to do, in Excel, I would have to do something like, I would have to do it differently. Here's what I would need to do if I were in Excel. So Excel, you can't make a function, right? but you know what x squared is. X squared is x times x. So I could go equals A8 times A8. That's squaring, right? Multiply something by itself is squaring, and then enter. And then click, left click and hold, drag. So when you're working in Excel, sometimes you have to be a little bit more clever about how you get your function, whereas GeoGebra just lets you make the function and then feed things into it. But they work generally the same. And both of them can give you a quick way to calculate anytime you're doing kind of tedious tables where you have to generate numbers repetitively. Is that okay? Anything else before we end?
I didn't know if you had a Zoom session yesterday since I didn't join. But on that homework paper, it said still to do it on colored paper.
That's a typo, so no colored paper.
Okay, I just wanted to make sure.
Well,
'Cause the
yeah,
last
no,
time we did-
it's I didn't get all, I saved an old syllabus and I didn't clean out all of those. I tried to and failed. So the colored paper is only on campus to keep people from stealing paper out of the copier machines on campus, but nobody's on campus.
Okay, yeah, I just remembered you said it wasted a lot of your
It
ink.
wastes a lot of ink. Yeah, when I get like, in the spring, I had like students submitting their homework on construction paper. And then when I go to print it, I get like a page of pink
But does that apply to our notes as well? Do you want them in plain white paper rather than lined
Then
paper?
I don't care on your notes because I'm not going to need to print them. I'll just be right on the homework. It's going to make a difference to me because I want to print it so I can put feedback on it and send it back to you. I want to write on it and give you something so that you know what I'm thinking about the work that you're doing. And I won't be trying to insult you. I'll just be trying to let you know what I'm thinking. On your notes, I can read them on my screen. I don't need to print them. I'm not going to.
Oh, I was gonna ask, how do we turn the homeworks in and the notes?
Scan to PDF. So if you need me to, I can in Remind send you the document that gives you directions for both iPhone and Android, how to use your smartphone to scan, if you don't have a printer that does scanning for you. We just scan to PDF and then send me a PDF document. I'll resend the instructions when we get out of class. Anything else? All right, let's get out of here then. What time is it? 6:30? That's an hour. All right, I'll probably get more questions tomorrow. That was a lot today. So that's good though. That's what we want. We want lots of questions. All right, guys, gals, have a good evening.
Night.
Take care.
Thanks.